So in our workbook, we've got cyclohexane conformations. We're looking at the bond angle that carbon prefers to form, which is 109.5 degrees, as compared to the angle of a hexagon, which is 120 degrees. Why is that? Why is cyclohexane more stable than anything else, even though that bond angle doesn't match up? Well, the reason is because these molecules are constantly in motion. What you should do now is make a ball and stick model of cyclohexane. And if you do that, you'll see it doesn't sit flat. It's not able to. And the molecule itself, on the molecular level, won't sit flat either. It'll actually make this sloping motion. And we're able to examine this in order to figure out what is the most stable cyclohexane conformation. If this thing is able to move and kind of wiggle around, what is the version of it that is the most stable, that is the ideal? Okay. We've got quite a few here in your workbook. We've got the chair conformation, the boat conformation. I think one of these is called a twist boat. We're really only going to look at the most stable conformation. You should be aware that these other ones do exist, but we're going to be focused on, can I draw the primary cyclohexane conformation? Because this is going to be its lowest energy state. This is going to help us see how reaction mechanisms could occur with cyclohexane. And we really want to get a good idea of how these molecules are able to twist and bend and move, so that when we look at things like a substitution reaction, which we will get into, we'll be able to see how these molecules will shift their shapes in order to react. In order to draw the cyclohexane chair conformation, it's named this because it's got that lounge chair kind of look. We're going to start with two dotted lines here. And what I'm going to do right off the bat is I'm going to draw two parallel lines kind of at about similar lengths. Here, draw about there. That's kind of similar. Okay. Next, I'm going to go from this point where my line meets my dotted line, and I'm going to draw up at an angle to the other dotted line. And I want to draw my second one parallel as close as I can get to. Okay. And I'm just going to connect my final lines. There's that. There's that. So we can see this kind of looks like a lounge chair. If you draw it better, it might look more like a lounge chair, but the point is this is the chair conformation, okay? Now we need to draw in our hydrogens. And we're going to have two types of hydrogens here. The first type is our our axial hydrogens. Our axial hydrogens are going to be sticking straight up and straight down, okay? So let's go ahead and get rid of our dotted line here so that we can draw these. Now, the axial hydrogens are going to go in the same direction as the corner that you draw it on. Each corner here is a carbon. So if you notice, this corner here is pointing down. My axial hydrogen is also going to point down, straight down, okay? Here's another pointing down. There's hydrogen. Here's another pointing down. There's a hydrogen. Okay. Next, axial is going up. And there we go. There's our axial hydrogens. Next, we need to draw our equatorial hydrogens. And these are going to be drawn at an angle between these points, okay? So if I drew an up hydrogen, my equatorial is going to be slanted down, right? So up hydrogen, slanted down, equatorial. Up hydrogen, slanted down. And up hydrogen, slanted down. Next, last three. Down hydrogen, slant the equatorial up. Down hydrogen, slant the equatorial up. Down hydrogen, slanted up. And there we have our chair conformation of cyclohexane. Now we can see here, we should be able to kind of visualize this now, that these hydrogens are all staggered from each other. If we draw a Newman projection of this, which we'll go ahead and do next, I have a paper to reference in front of me. Right there. If we draw a Newman projection of this, then I get something like this. Okay, and the rest of these should be H's. There we go. There's our Newman projection for our cyclohexane in the chair conformation. We can see that our these should be CH2s. We can see that our two middle carbons are staggered from each other. They are staggered away. This is looking at this perspective. So we're looking at these are my front two carbons. These are my back two carbons. I can see that this is this CH2 and this is this CH2. So all of my molecules are as staggered as they can be, as well as maintaining in this position a 109.5 degree bond angle. So the cyclohexane is able to maintain as close to absolute stability as it can in this conformation. All right? So we should be able to draw the chair, and we should be able to draw the Newman projection of the chair. Okay, so you might need to practice that a few times.